In this section, we're going to talk about some new functions for us called the hyperbolic functions. And so to start off, we're actually going to start off with a visual. And what we're going to do is we're going to think about taking something that a string or a chain, like a necklace, something that you can hold, one in each hand and just sort of dangle. So there's nothing but the weight of the chain or the string or the rope hanging between your two hands, like I have this image right here. This is just like a little necklace. If you were hanging this, you would think at first glance that that might be a parabola, that shape is a parabola. That might be your first guess. And it turns out that that is actually not correct. This is actually the shape of a hyperbolic cosine. This is called a catenary curve, the shape of a flexible chain or cable supported on both ends, with only the uniform gravitational force of its own weight pulling down upon it. This is what we call this catenary curve, and it is actually mathematically modeled by what's called the hyperbolic cosine. And so we're going to get into all of that, and we're going to talk about how this relates to, how these functions relate to the trig functions, and you'll see with their names, there's the hyperbolic sine, hyperbolic cosine, hyperbolic tangent, that of course, given those particular names, that they likely do connect in some way to the trig functions. So we'll talk about the relationships there, as well as this idea of hyperbolic. Where does that come from? Well, that's because they're also connected to the unit hyperbola. And so we're going to talk all about that and explore these a little more, but just to see where they occur in nature, where this curve actually occurs in nature. Or in the more natural world, engineering world, more natural world. One is the St. Louis Arch in Missouri. The inverted catenary arch is handy because it actually supports itself. So many architects have actually used that in their work over time. So the St. Louis Arch in Missouri is one of them. Turns out that actually suspension bridges, and this is a very early image of the Golden Gate Bridge, and it turns out that suspension bridges, the cables, the suspension cables themselves right in here, before the bridge is attached, which is this image right here, are actually in the form of these catenary curves. They are modeled by hyperbolic cosines. Now, as soon as the bridge is actually hung from those suspension cables, which you can see down here, this is right as the bridge is being built and hung from the suspension cables. When the bridge is hung from those suspension cables, then it has the weight of the bridge, and it actually pulls those suspension cables into a parabolic model. So then once suspension bridges actually have the bridge attached to the suspension cables get pulled into a parabolic model mathematically. It's kind of interesting. I always find that interesting that when they're hung without the weight of the bridge, only their own gravitational force, they are modeled by a hyperbolic cosine. But once we've pulled the weight or put the weight of the bridge upon those suspension cables, then it's not just the gravitational force of their own weight, then they are also pulled into place and into a parabolic curve by the weight of the actual bridge. So also kind of interesting. And here's another example, another visual. Probably not going to say the name right, this Sagrada family in Spain. The architect Gaudi made these, and there's lots of catenary arches within his architecture. Okay. So let's get to the mathematics of it. Now that we have a little introduction, let's get to the mathematics of it. And it turns out that specific combinations of e to the x and e to the negative x are related to the unit hyperbola. This is where the hyperbolic name comes from. They are related to the unit hyperbola, x squared minus y squared equals 1, remembering that the unit hyperbola, if we could just draw it, is this, the unit hyperbola is that shape right there. I'm going to pull it up in just a second too on an image, but that's the unit hyperbola. And it turns out that these specific combinations of e to the x and e to the negative x that are defined below are related to this unit hyperbola in a way that is very similar to how the trig functions are related to the unit circle. So remembering that to the unit circle, sine and cosine are related to the unit circle, and our now hyperbolic functions that I'm going to define are going to be related to the unit hyperbola. So that's where this name comes from. So a little explanation of where it comes from, and then I will show you how it is related to the unit hyperbola after we've defined them. So the hyperbolic sign, and the way we denote that it's a hyperbolic sign and not a sine is by using sine, S-I-N, for sine, and then adding the h. So this, when we read this, this reads the hyperbolic sign of x is equal to e to the x minus e to the negative x over 2. Let me zoom in a little bit. Okay? Now, we can also say sinh. Sometimes you can hear the word sinh, like this, the sinh of x that is understood to be the hyperbolic cosine. So notice this is really just a combination of two functions that we've already worked with, e to the x over 2, so 1/2 of the exponential growth function, minus e to the negative x over 2. So that's really a combination of two functions that we've already worked with. We're just giving it a new name. It's called the hyperbolic sine. So just keep that in mind as well, because we're going to do all kinds of fun things with these hyperbolic functions in this sections, take derivatives, look at their inverses, take derivatives of their inverses, and all of it kind of is going to come back to the fact that they're defined by these exponential functions, and we know how to work with exponential functions. So we're really just working with a specific combination that we're giving a new name, a hyperbolic sine. Okay, hyperbolic cosine, or cosh of x, is e to the x plus e to the negative x over 2. Notice the similarities here. The hyperbolic sine has a minus, and the hyperbolic cosine has a plus. Now, the rest of the hyperbolic functions are connected to the hyperbolic sine and hyperbolic cosine. So the hyperbolic tangent of x is the ratio of the hyperbolic sine over hyperbolic cosine. So you see that ratio right there. And the hyperbolic cosecant 1 over sinh, hyperbolic secant 1 over cosh, and hyperbolic cotangent is 1 over hyperbolic tangent. And so you can see those combinations. So these, again, let me zoom out a little bit so you can have the full picture here, but these are worth writing down and keeping in your notebook so that you have your definitions for your new set of functions. So we're adding these to all the functions that we've already have in our toolbox, right? We've got all of our trig functions, we've got all our polynomials, our rational functions, root functions, and all the combinations of them, the exponentials, the logarithms. I'm trying to think if I'm missing anything, our inverse trig functions. We have a whole bank of functions that we work with, and we are now adding the hyperbolics, the hyperbolic functions. Okay, so let's just take a little side tangent. That was a little joke right there, since we are headed into talking about trig functions, a little side tangent here. Okay, so let's talk about how the trig functions are related to the unit circle and how the hyperbolic functions are related to the unit hyperbola. So I want to take a moment to talk about that so that we have kind of a big picture view of our hyperbolic functions. So here's just a little recall from our trigonometry. All the trig functions come from terminal points on the unit circle, where the points on that unit circle can actually be defined. Any point on the unit circle xy can be defined as cosine of t, sine of t, x being cosine of t, y being sine of t, where t is actually the arc length to that point. It's the arc length in radian measure traversed along the unit circle, and that gives us that point. Okay? And it turns out, since this is on the unit circle, x squared plus y squared, which is cosine squared plus sine squared, is equal to 1. And that's our Pythagorean identity for the trig functions. So we know that sine squared plus cosine squared equals 1. And that comes from our unit circle, just our unit circle relationship. And that's an identity that you've used extensively, so one that you know. And you can create all the other Pythagorean identities simply by dividing by sine squared or cosine squared and simplifying. Okay, so that's how our unit circle and our trig functions are connected. How then is the unit hyperbola and our hyperbolic functions related? Well, here is our unit. Here, right here, is x squared minus y squared equals 1. Here's our unit hyperbola. X squared minus y squared equals 1. We can see the unit hyperbola right here. And it turns out that if we were to define t to be twice the area of this little shaded region, so if we actually see that shaded region right there, t is equal to twice the area of the shaded region. So if t is twice the area of the shaded region, then the points on this right arm of this unit hyperbola, the right branch of the unit hyperbola, are defined as cosh of t, sinh of t, so where t is twice that area. And so if that were the case, if that's what x and y are, if we plug in x and y, we get this first identity that connects our hyperbolic functions. So it turns out that cosh squared of t minus sinh squared of t is equal to 1. The hyperbolic cosine squared minus the hyperbolic sine squared equals 1. Whereas with the trig functions, the the trig functions versus the hyperbolics, when you add cosine squared plus sine squared, you get 1 because it's connected to the unit circle. But when you take hyperbolic cosine squared minus hyperbolic sine squared, you get 1 because they're connected. These hyperbolics are connected to the unit hyperbola. Okay, so there's a very big picture of what these hyperbolic functions are and how they are related to the unit hyperbola. So want to kind of keep that in mind because there's all kinds of interesting connections that come, and if we always just kind of think, well, like how did that work with the trig functions? It's going to work in a similar way with the hyperbolic functions, but they're connected to the unit hyperbola, not the unit circle. So that's where, you know, some of our identities, you'll see slight differences in the identities because it's a unit hyperbola instead of a unit circle. Okay, so let's get into the nitty-gritty of each of these individual functions now. So we've got our graphs of the hyperbolic functions, and I want to talk about what the hyperbolic functions look like. And to do that, I want to actually go into their exponential expansions. So let's consider those two exponential functions, e to the x and e to the negative x, and let's talk about how those give us these hyperbolic functions. So this red graph that you see right here is hyperbolic sine. So this is y equals the hyperbolic sine of x. And it is a combination of e to the x minus e to the negative x. It's an addition, or it's actually a subtraction of two exponential functions, an exponential growth function and a reflection of an exponential decay function. Okay, so let's look at where these exponential functions come from, or where these hyperbolic functions come from the exponentials. So the hyperbolic sine of x is defined to be e to the x minus e to the negative x over 2. So if we consider what each of these functions look like, and so in blue right here, I'm going to have graphed e to the x over 2. So in blue, you can see that exponential growth curve. And if we look at what we've got going on in green here, in green we have e to the negative x over 2. So those are those curves. Those curves are graphed there. Let's zoom in a little bit here. And so if we were to think about subtracting those, what you can see is, I can put this up here, if you can see sort of the visual here, if we're going to subtract those two curves, you can see that at 0 we would be passing through 0. If I could get this. Oh, I can't actually, I'm sorry, I was trying to draw on my Desmos graph, but I can't draw on my Desmos graph. I can't draw on my Desmos graph because I'm actually in a web browser. Sorry about that. I was trying to draw on the graph, but I can't draw on the graph. So what you can see though is at 0, so when x is actually 0, our hyperbolic sine curve, because we would subtract these two and they're equal at 0, so we would be passing through 0. And if as we move to the right, as my exponential growth grows, my exponential decay is decreasing, obviously there. And so what's going to happen is that exponential growth is going to dominate this difference right here. And so this part's going to get small and this part's going to get big, and dividing by 2, we're going to see that exponential growth dominate. And the same thing on the opposite side. And so when we subtract, what we end up getting, and we can do this, I have this set up to do, and so we can look at it, is we can see the actual hyperbolic sine curve coming from the difference between those two. And if we use this slider right here, we can actually see moving along the curve as we're doing that. So we can use the curve and see those two, the combination of those two curves, generating this curve that if we zoom out, what I want to do is I want to zoom out and look at it. Notice how as that exponential decay, as e to the negative x, essentially we're subtracting off an exponential decay function from an exponential growth function. And what you're seeing is it's almost like an asymptote. I mean, it's not a linear asymptote, but what's happening to that e to the x for this hyperbolic sine is it's almost acting like an asymptote. And if we were to actually flip the green curve and look at the minus curve, we would see that same asymptotic behavior down here. So the hyperbolic sine has this shape. The hyperbolic sine curve has this shape that looks kind of like this, where these two ends are behaving like exponential growth curves, positive exponential growth curve and a reflection of an exponential curve on the left side. And so we're getting that general shape as we look at those, that hyperbolic sine curve. So it turns out that the hyperbolic sine has a domain of all the real numbers. So you could also say that the domain is from negative infinity to infinity. It also has a range that is from negative infinity to infinity. So you can see that hyperbolic sine curve right there, just in another graphical model that I have here on the screen. You can see that red curve, that hyperbolic sine curve. Now, if we take the same two curves, and I just noticed a typo on my screen, if you take the same two curves, e to the x, and you add, the hyperbolic cosine is defined to be the addition of e to the x and e to the negative x. If you add those two exponential curves and divide by 2, what you end up with is a curve that looks, and remember we had at the beginning of this video, I talked about how certain architecture and certain bridges, suspension bridges, and if we were to hang a rope or a necklace and it has only that gravitational force, you might think it's parabolic, but it's actually a hyperbolic cosine, and that this is that hyperbolic cosine. So in red right here we have the hyperbolic cosine, y equals the hyperbolic cosine of x, has this general shape. And again, you can see as and honestly, we're not very far out on the graph here. On the x-axis, we're only looking at this graph from -2 to +2, and you can see how it just starts to essentially this tiny amount of exponential decay right here. When I add that to an exponential growth curve, it doesn't put me much above it. So this hyperbolic cosine is sort of bounded in here, almost like asymptotes, by those two exponential curves, and you can see that graph right there. So the domain, turns out that if you add two exponentials, though, since exponentials are always positive, this is always going to be a positive function. Not only is it always positive, it never goes below 1. It hits 1, but never goes below. So the domain for the hyperbolic cosine, this new curve that we're talking about, the domain is all reals from negative infinity to infinity, and the range, I did give that as a interval there too. So the range is from 1 to infinity. So there's our hyperbolic cosine and our hyperbolic sine. And if you want to pause for a second and graph those and state their domains and ranges, they are worth knowing what the graphs look like. It's sort of like knowing sine of x and cosine of x and having those in your tool bank. It's worth having an idea of what these two curves look like. Now, the hyperbolic tangent, which is the ratio of the hyperbolic sine over the hyperbolic cosine, turns out is actually bounded in its range between -1 and 1. So it actually has horizontal asymptotes of y equals 1 and y equals -1. And so here is what the hyperbolic tangent looks like. And again, it starts to behave an awful lot like those asymptotes, pretty close to 0, pretty much in the center of the graph. And so you can see those horizontal asymptotes at the top and the bottom of the graph right there. I realize that one didn't look like a straight line. I didn't pull out the ruler. So there we go. So there is our hyperbolic tangent curve. In a lot of ways, it looks like the inverse tangent curve with different asymptotes, but it is not. This is the hyperbolic tangent. Okay, so that is our introduction to our hyperbolic functions. And I will just leave with, that's our graphs and our introduction, and I will leave with just the definitions on the screen again. I'm going to end this video here because we have to come back and talk about the identities, and I want to spend some time proving an identity or two just so we can see the use of these functions, and then we got to get into the calculus of the hyperbolics. And so I'm going to put those on another video, so we'll end right here just with the definitions of the hyperbolics. So our new 6 functions that we can work with now are hyperbolic sine, hyperbolic cosine, hyperbolic tangent, and then of course the reciprocals of all 3 of those. Remembering that when we see these hyperbolic functions, you know, when you see sinh or cosh in an expression or an equation, that they are defined as combinations of exponential functions, and that they are also related to that unit hyperbola. So remembering those sort of things in this introduction, those are useful things to have in mind when we come across these hyperbolic functions.